Okay, welcome to this second session of short presentations. So we have four papers, each presented 15 minutes. We start with Rahel Rickenbach from ETH. So over to you, Rahel.
So thank you for the introduction, and welcome to my presentation, Inverse Optimal Control as an Errors in Variables Problem, a project that I did in collaboration with Scampicchio and Melanie Zeilinger, which are both here today. I would like to start this presentation with a motivating example that consists of an autonomous car on a street surrounded by some obstacles like trees with which we do not want to collide. So this describes an application where we're interested in safety, but maybe also in performance. So we might want to race or we might want to stay close to the center line. And now such a situation can be addressed with an optimization-based control strategy where we can consider the environmental information and the constraints, but also then we can, by designing a suitable cost function, tune our performance. However, designing such a suitable cost function can be cumbersome, unintuitive, and also its tuning can be difficult. Now, to address such an issue in situations where we have access to some optimal demonstrations, they might be provided from a human demonstrator or from other sources. The field of inverse optimal control provides us with some tools that allow us to estimate this cost function or some parameters of it from those optimal demonstrations. And now within this talk, we're going to consider a specific problem description where we have an unknown objective parameter theta with some known basis vector phi. And we further assume that the environmental demands as well as the dynamics are known. Now, this task has not only been investigated by the optimal control community, but also from the reinforcement learning side. And while now the approaches in the inverse reinforcement learning direction, they allow for, by their problem formulation, for natural consideration of suboptimal demonstrations, looking into inverse optimal control and some of its approaches, we actually have this natural consideration of inequality constraints that can be active or inactive. And now, as a goal of this project, we try to investigate what happens if we take a look at this inverse optimal control tools and use them with suboptimal demonstrations. We therefore focused on the tool of inverse Kouchner-Tucker estimation, which, as its name already says, builds upon the Kouchner-Tucker conditions, which provide us with necessary conditions for the solution of an optimization problem for of a large group of optimization problems. And they consist of the so-called stationarity condition that sets the gradient of the Lagrangian equal to 0. We have the complementary slackness, making sure that our dual variable lambda multiplied with the corresponding inequality constraints evaluates to 0. And finally, also primal and dual feasibility. And when we now work with an optimal demonstration, what we can actually do is insert this optimal demonstration in those conditions and solve for our unknown parameters theta and lambda. Now, when we work with suboptimal demonstrations, then unfortunately, most of those conditions are violated. And especially the stationarity condition might not even evaluate to 0 for any parameter combination. How this is now addressed in traditional inverse KKT estimators is that one looks at the relaxed version of this problem. So we have an optimization problem that we solve for the unknown parameter theta and lambda, where we have in the objective a least square approximation of the stationarity condition, and we consider the remaining conditions in the constraints. So we have complementary slackness and dual feasibility. However, if we now take a closer look at this approximation, then we can see our stationarity condition for the specific problem class, where we are linear in the unknown objective parameter theta, then we can rewrite this as a regression problem, where we have with j theta now our objective Jacobian, with j lambda our constraint Jacobian, which describe our feature vector j that depends on u. We have our regression vector beta, which is stacked with theta and lambda, and they evaluate to a 0 vector, which is our dependent regression variable. When we now consider suboptimal demonstrations, then we actually have an error on our independent regression variable, and this describes a so-called errors in variables problem, for which naively square estimators are in general not consistent. So what we did is we also looked at the inverse KKT estimator, but as an error in variables problem. So we considered two different problem classes. The first one is some Gaussian additive noise, where we have zero mean but an unknown covariance. And we looked at the second problem class, where we also have additive noise with zero mean, but we do not know anything about the distribution. For both of these problem classes, we provide two optimization-based approaches that reflect the quality of the estimate in the objective function and consider the remaining KKT conditions in the constraints, kind of similar to what you've already seen with the traditional relaxation, but they are consistent for linear quadratic problems. So let's have a look at the first problem class, which we address with a maximum a posteriori approach. So here, what we do is we take, once again, a look at the stationarity condition. We transform it into the spatial network, where we now have beta and u as Gaussian random variables. Sigma u is also a random variable, so remember this is the unknown covariance of our suboptimality that we add. However, this is inverse Richard distributed. And then we have ud and yd as realizations. So ud are our suboptimal demonstrations, and yd is actually a disturbed version, artificially disturbed version of the zero vector of our stationarity condition. So sigma y is a hyperparameter. With this model, we can also introduce some prior knowledge. So if we already know something, maybe from a previous solution, we can directly integrate that, and then we also solve an optimization problem where we now maximize the posterior. So what we do is we jointly optimize for beta and u and minimize the negative logarithm of the posterior in the objective. We consider the remaining KKT conditions in the constraints, and we obtain an estimate of sigma u by using a stochastic sampler. When we have a linear quadratic case, we rely on the Gibbs sampler, and otherwise on the Metropolis-Hastings sampler. For the second problem class, we cannot leverage any knowledge of any distribution anymore because we don't have it. That's why we resort here to a total least squares approach, where we now minimize the squared sum over all residuals. So we consider now the suboptimality as residuals, meaning we can write the following optimization problem. And because we know that there is actually an optimal solution, we can reformulate this optimization problem to get rid of some optimization variables and reformulate it like this. So now we also jointly optimize over u and beta, consider the KKT conditions in the constraints, and we obtain an estimate by an expectation maximization inspired approach, where we kind of iteratively, empirically approximate this sigma u. The consistency guarantees for both of these optimization-based approaches, they both rely on a reformulation of the objective, where we leverage the law of large numbers, such that the global minimum of our optimization problem actually lies at the optimal solution. And then for these linear quadratic problems, we actually end up with a biconvex problem, where we know that there exist some solver strategies for which we actually have guarantees to converge to this global optimal solution. And in addition, for the first problem, where we also use some stochastic sampler, we rely on the ergodic theorem. However, maybe some of you have already realized that when we solve these problems, we always solve a so-called mathematical problem with complementarity constraints that can be challenging for standard solvers. That's also why we relied on an adapted version of an interior point method. We tested our approaches not only on linear systems, but on three different systems in simulation. So we have a linear spring damper system, as well as a nonlinear kinematic bicycle model. For both of them, we added suboptimality as zero mean Gaussian noise. So we relied either on the Gibbs sampler or the Metropolis-Hastings sampler, both belonging to the first problem class. And then we also looked at the biomedical system, which is kind of modeling of the glucose insulinic cycle in the human body. And as here, the insulinic input can never be negative, but it's actually very often close to zero. Modeling the suboptimality as Gaussian would not have made sense. So that is why here we employ the approach from the second problem class. Now, looking at the results from the kinematic bicycle model, we can see that for an increasing value of sigma u, so an increasing value of suboptimality, as well as the mean estimate, as well as standard deviation for 10 experiments, we see that our approach at the bottom outperforms the traditional relaxation approach by quite a bit. And if we only look at the theta estimate in the mean, we can see that we have a mean estimation error reduction of 81%. And also for the other systems, we could achieve a mean estimation error reduction of quite a bit. Now, to sum up, what we did is we investigated the inverse KKT estimator as an error in variables problem. We presented optimization-based solution strategies for two different problem classes, one being Gaussian additive noise, the other being additive noise with an unknown distribution. We provide consistency guarantees for linear quadratic problems. However, our approaches still rely on the solution of a mathematical problem with complementarity constraint, which can be cumbersome and is definitely something we would like to address in the future. However, testing them in simulation, we could see that we actually outperform the traditional relaxation approach by quite a bit. And with that, I'm at the end of my presentation. I would like to thank you for your attention.
Thank you. We have time for a question. Any questions? Maybe I can ask, can you say something about how you used an interior point solver to deal with the complementarity constraint?
Yeah, so the thing is that generally it is not, they can fail when you have this complementarity constraint. So there are some methods in the literature that relax this complementarity constraint, and then it's not an equality constraint anymore, but it's then an inequality constraint with a slack, and then you kind of iteratively reduce the slack such that the solution improves.
Okay. If there are no questions, then let's thank the speaker again. Okay, so our next speaker is Leonardo Toso from Columbia University.
Okay, so yeah, thank you for the introduction. Hello, everyone. Today I'll be talking about meta-learning for control. So meta-learning, in particular model-agnostic meta-learning, has shown to be efficient for many fields of application. For example, reinforcement learning. And in this work, we try to understand whether or not meta-learning is the correct solution for learning controllers that can quickly adapt to unseen tasks for the model-free LQR problem. But first, let's understand what actually is this idea of meta-learning. So meta-learning, or learning to learn, is this concept of training a model on a variety of tasks such that this model can quickly adapt to an unseen task. For example, we have a multitask data set composed of text, images, audio data, or state input observations that we collect by playing with a drone. A huge effort in the machine learning community these days has been made towards training these models that they call foundation models, for example, GPT, Llama, Sora, that can quickly adapt to an unseen task, for example, question answering, as ChatGPT does. And this adaptation is made with a reduced amount of data. This can also be a task, an unseen task of a robot arm manipulation, object detection, sentiment analysis, image classification, and so on and so forth. So by following this trend of success of meta-learning, especially in the reinforcement learning field, why not to consider meta-learning for control, where you have a linear dynamical system that describes the dynamics of a drone that is flying over this desert forest, where the conditions in this environment is parameterized by some parameters Q and R. And the objective here, in order to control this system, is to design a control sequence that minimizes the cumulative cost that depends on the system and on the environment. But how nice it would be if we have like similar drones flying over different environments, and then we can collect this data to have a diverse multitask data set, and then exploit this diversity to learn a control sequence that can quickly adapt to an unseen task or unseen system in an unseen environment. For example, a different drone that is flying over the Amazon forest environment, for example. This motivates the question, can meta-learning actually provably learn LQR controllers that can quickly adapt to unseen tasks? And I'm going to provide a positive answer for this question in this talk. We'll also emphasize that we are considering LQR here as a baseline for more complex control problems. But first, let's understand what this MAML or model-agnostic meta-learning is actually optimizing. So if you have a bunch of tasks that are being drawn from the same task distribution, where each task has its own data set composed of features and labels. And each task is also equipped with a cost that is parameterized with a parameter theta and also depends on the data set. Finn et al. A few years ago, they proposed this method called MAML, model agnostic meta-learning, where they tried to learn a model initialization by solving that this meta-learning cost that is just an average across all the task-specific costs, but now it's subject to one step of policy gradient in the argument or more steps of policy gradient. In this work, we just consider one step. As we can see, this is a bi-level optimization problem. We have an optimization over each task-specific cost and also in this average. So they propose that if you use a policy gradient method to solve both inner and outer optimization, you're gonna, and then we repeat this for some iterations, you're gonna find a solution that is close to each task optimal parameter. But although the success, despite of the success of MAML for many fields of application, there are just a few works trying to shed the light on the convergence and adaptation guarantees for the meta-learning. For example, trying to characterize the distance between this learn model and each task optimal model. And this is even more limited to the control setting. Okay? So this is why we're going to consider our friendly LQR problem, where we consider a linear system, and the objective here is to design a controller, Ki star, that parameterize the control inputs and minimize the quadratic cost on the state and inputs of the system, where this cost is parameterized by some matrix Q and R. Its optimization is over stabilizing set K. Okay. So if we have the system matrices and the cost matrices, this is a very well-established problem. It's a model-free LQR. We just need to solve a required equation. But what if we don't have the system matrix, the cost matrix, and we're under a model-free learning? Well, of course, this story that I'm telling here should definitely cross paths with policy gradient, since they are more flexible methods for the model-free learning setting. You don't need to estimate the dynamics of the system. You just need to estimate gradients. And Professor Fazel et al. A few years ago, they proved that the policy gradient method can actually converge globally to the optimal solution for the LQR problem. So if you give an initial stabilizing controller for a controllable system, and then you repeat policy gradient steps by either using the true gradient or an approximated version of the gradient, you're going to converge to an absolute near optimal solution for the LQR problem. And this is mainly due to this nice property of the LQR cost, which is the gradient dominance, that provides us with some results that are analogous to the strongly convex setting for non-convex functions. There are some other nice properties of the LQR cost that we also need for this global convergence. And we usually define this stabilizing sublevel set just to show that for each iteration of our policy gradient, you're going to have a stabilizing control. So we're going to fix our focus on this stabilizing sublevel set instead of the stabilizing control set. Okay. As I mentioned before, we can do this either with an estimation of the gradient or the true gradient. We're going to use a zero-order estimation to estimate gradients and hashes for the MAML later. I'm not going to enter into many details about the zero-order estimation here, but it's very simple. We just need to perturb our controller, our recurring controller, with a matrix that has Frobenius norm R, where this R is usually called smoothing radius. And then we do this m times for m trajectories. We play the system with this perturbed controller, collect data, and then a zero-order estimation type of approach is going to give us estimation for the gradient and the hashing. Okay. Okay, but this is what I'm talking here is just a single task LQR. And if we just learn to control the system one, the task one, the system flying over the environment one, by just using their data, and then try to use the controller that we learned for a different task, doing this in a single task setting doesn't provide any adaptation guarantees. We don't know if our controller that we're learning is going to adapt to unseen tasks. So the idea of using MAML in this approach for the model-free LQR problem is to provide these guarantees. Okay. This is why we consider this setting where we have LQR tasks that are tuples, system and custom matrices, and each task has its own objective of finding this controller Ki star that minimize a task-specific cost. We measure the heterogeneity across all the tasks, and now as a worst case setting. So we consider the spectral norm of the difference between the matrices, and we assume that they're all bounded by some heterogeneity levels. So our objective is to design this controller K star sub ML, which is the MAML optimal controller that is going to minimize this MAML cost here. That is, as we have seen before, is just the average across task-specific costs, but now we have the argument a one-step PG. And we do this over a stabilizing sublevel set, which is the intersection between all task-specific stabilizing sublevel sets. If we do this with a policy gradient MAML type of approach, we just take the gradient of the MAML cost, and then we have Hessians and gradient estimations come into play. Just to recap, our objective, which is different from some papers in the literature, we are not the first one to apply MAML to LQR, but we're the first one to review in our bounds the ultimate objective of MAML, which is the quick adaptation. So we want to characterize that if we learn a controller and we plug to any task that comes from the same distribution, this controller will also do well. So it's just a policy gradient steps from the optimal. But the difficulties here are the following. We need to produce stabilizing controllers for all the tasks, every iteration of our policy gradient method. We also need to control gradient and Hessian estimations now. And more importantly, the non-convex landscape of the MAML, and now the PL or the gradient dominance doesn't hold. Just to illustrate this, if you have a scalar instance of LQR, which in this case the LQR is actually convex, here in green and orange is the LQR cost. Even for the simple instance, the MAML is highly non-convex, okay? And this is due to the heterogeneity across the tasks. And we're going to measure this heterogeneity in our bounds by this result that we provide in our paper, which is for any two distinct tasks, if we measure the spectral norm difference between two task gradient evaluate at the same controller for a stabilizing controller, this is going to be bounded by a function that depends on the heterogeneity level across the tasks. And this case encompasses system heterogeneity, cost heterogeneity, system and cost heterogeneity. And we're going to show later that if this heterogeneity is small, then the MAML controller is close to each task optimal controller. Okay. So our algorithm is quite simple. An initial stabilizing controller, we give an initial stabilizing controller, then we set inner and outer step sizes and also the parameters for the zero order estimation. Then for all the iterations and all the tasks, we first estimate gradients and Hessians, then we do this inner step PG, as I mentioned before, then we compute this Hessian term as well. Then for all the tasks again, we now estimate the gradient, but at that inner step PG, and then we update the controller with an approximate version of the MAML gradient. Okay. Just to recap again, the purpose of this work, which is different from some works in the literature, is to provide the guarantees that the learning controller that we learn after any iterations is going to be close to each task optimal controller, and also each task optimal controller is going to be close to the MAML optimal. So we know that our algorithms converge to the optimal solution of the MAML problem. Our convergence guarantees are the following. If we have an initial stabilizing controller, and then we set the parameters accordingly, we provide the conditions, the detailed conditions in our full paper. Then with high probability, we show that the learning controller is going to be absolutely close to the optimal, each task optimal controller by this heterogeneity term here. Okay, so the heterogeneity across the tasks impact the learning controller. Also, each task optimal controller is going to be close to the MAML controller by also a heterogeneity term. And just the main takeaway here is after a sufficient large amount of iterations, we're going to converge to a region that is close to each task optimal controller and is also close, where each task optimal controller is also close to the MAML optimal controller, where this closeness is defined by the heterogeneity across the tasks. Okay. For the stability, initial stabilizing controller again, set the parameters of our algorithm accordingly, where the conditions are in the paper. Now, if the heterogeneity is small, then we can provide stabilizing controllers for each inner and outer step policy gradient. The main takeaway here is if we control carefully our inner and outer step size, the inner and outer policy gradient updates will never leave the stabilizing sublevel set with high probability. Okay. Just to validate our results, here we consider a setting with 50 heterogeneous LQR tasks where each system has 4 states and 2 inputs. Then we report here the gap between the learn controller with respect to the iterations and the task-specific, the first task optimal controller, and we see its conversion to the task optimal controller, but with a bias where this bias actually increases when the heterogeneity increases, as predicted in our theory. And also for the adaptation part, we just use the learn controller after 200 iterations, and as an initialization of a policy gradient method, and then we see the quick adaptation, which it doesn't happen if you use a random initialization. Okay, so the idea here is to use this learn controller to quickly adapt to the optimal controller of each unseen task. Just to wrap up, we consider this a problem of learning in a quadratic regulators that can quickly adapt to an unseen task. We are the first to provide these guarantees that shows the ultimate goal of MAML, of meta-learning, which is learning controls that can quickly adapt to unseen tasks because they are just a few steps away from the optimal controller for each unseen task. And we also show that our learning controller is stabilizing for the underlying systems. I'd like to thank my collaborators, and that's it from my side. Happy to take questions.
So, do we have any questions? Yes.
Interesting work. I have one question about your condition. So you started AI, AJ, like it's a discrete set of the choice of dynamics. So I kind of feel like your approach, probably you can just go ahead to make it be a continuous range. I'm talking about like you have the A, you have
Yes.
the choice of the task. The task says that it can be even in a continuous region. Is that true or no?
Oh,
So,
you mean,
yeah.
yeah, sorry, I cannot hear you very well.
So my question is, so from the presentation, you're talking about A1, A2, A3, right? It's a discrete task, but the tasks are very close to each other, but you need the close to each other. The question is, can you extend this kind of condition to be just continuous set of tasks? Just like it's a set of A, but the diameter of the A, right, is kind of smaller than epsilon.
Yes, excellent question. Yes, you can do that. Actually, in our condition for the heterogeneity in the stability theorem, this heterogeneity bound here that says, okay, each task is close to each other, as you mentioned, and they are discrete, they actually depend on the parameter that is the stabilizing, where we define the stabilizing sublevel set. So you can have a continuous, like, tasks that are, they need to be close to each other according to that parameter that you define in our stabilizing set. But yeah, this can be the next step of our future work.
Great, have this slide. So then my question is, you have the stable outer as a summation of all those tasks. Once you change to be the continuous one, can you just pick find the set from the set, or you need to do the integration?
Yes, you can like, from a continuous set, you can select a finite amount of tasks and then do this. Is that the idea that you were?
That's my question, yes.
Oh, okay, yes, you can do this, definitely.
Okay, yes.
Okay.
Thank you.
Thank you. One more question.
So, you know, this idea of generalizing to multiple tasks is certainly an intriguing one. But, you know, the theorems that you quoted with Fazal, these are all about the t tends to infinity versions of LQG. Well, it seems to me that the problems that you really want to solve are where there's a transient before t tends to infinity. And my concern is that you are doing, you know, you're iterating among the stationary solutions of the Riccati in the choice of AIs. Whereas if you were actually flying between trees, you know, the transient is everything. It's not the, and I think in that other paper of Finn, Chelsea.
Yeah. Yes.
I think she also, she was less interested in the steady state. So the questions to you is, so you can get theoretical guarantees because I think you're doing the t tends to infinity. But if you're trying to do the transient, I think the meta learning, think it'd be I don't know, maybe you can prove things about them, but tell me what you think.
Yeah, that's an excellent question. So yeah, we haven't looked at this steady state that you were mentioning. We are definitely providing these non-asymptotic guarantees, which is not asymptotic, it's just for the transient. So yeah, yes, I think the work, the literature that we have so far, it's just for providing these non-asymptotic guarantees. And if you have the trees in the environment that you just mentioned, maybe it's not going to work. From the reinforcement learning setting, it seems to be quite robust, where you can have working very well this kind of approach. But there is a gap between the reinforcement learning and the control that we need we also need to look at. And but I think this result tries to shed the light at the guarantees first, and then consider more complex setting as you mentioned.
Okay, I think in the interest of time, we need to move on to the next speaker. So thank you, Rahel. It's HDMI here, I think. Okay, so our next speaker is Bruce Lee from University of Pennsylvania.
There we go. Okay, thank you for the introduction, and thank you everybody for being here. I'm excited to present my work studying adaptive control in the presence of model misspecification. Okay, the work that I'm going to present is the result of a collaboration with Anders Rantzer and my advisor, Nikolai Matni. So adaptive control has a wide range of applications. I'm just going to highlight a couple of them to motivate the study that we perform. One of the early applications was in flight controls, where it's necessary to adapt the controller parameters in order to account for the changing dynamics that occur as you change altitude or as you change flight speed. Recently, there's also been efforts to apply adaptive control in agile robotics, basically trying to achieve higher performance by adapting to the current environmental conditions. Now, one of the primary challenges in adaptive control is that the systems might change very quickly, requiring you to adapt to the current operating conditions with a very limited amount of data. The practical and commonly accepted solution to this is to try to reduce the complexity of the adaptation module as much as possible. So in particular, you can isolate a few parameters that you expect to vary during the operation of your system. If you use first principles models, this is a very conventional way of approaching this solution. So for instance, in aircraft, you might keep the entire model fixed and then just adapt the altitude and speed parameters. If you don't have first principles models, you can try to learn by collecting data from various operating regimes and then learning a pre-trained representation that captures what stays the same across all of the operating regimes. Then you just fine-tune the representation or adapt it to the current operating conditions. Okay, so this has been applied in some robotics works that have come out recently. Now, of course, the challenge with this practical solution is that by reducing the complexity of the adaptation module in this way, you may induce some form of misspecification or an inability to represent the underlying data generating process. Okay, so we have this practical challenge where we want to adapt with a very limited amount of data from the current operating conditions, and this rather simple solution where we reduce the complexity of our adaptation module, which may result in misspecified model classes. Okay, so we're motivated by this challenge and the practical solution to try to analyze and understand how much misspecification you should be willing to accept in order to reduce the complexity of adaptation. So with that, our goal is to rigorously study the impact of misspecification on adaptive control through a simple case study of the self-tuning linear quadratic regulator. Okay, so this kind of adds a bit of depth to the current analysis studying the self-tuning regulator. Okay, and one of the primary takeaways that we find is that there's somewhat of a phase shift between easily identifiable and not easily identifiable model classes. And what this implies is that if you are in a situation where you can, there are situations where you can introduce a small amount of misspecification in order to drastically reduce the complexity of adaptation. Okay, so with this motivation in mind, we're going to start off by just outlining the problem with the definition of the self-tuning regulator problem and our description of the misspecified model class. we'll use this to define our algorithm, which is designed basically to obtain our theoretical guarantees on the regret. At the end, if we have time, we'll look into some numerical validation, basically checking that the regret bounds we find are indeed what happen in practice. Okay, so let's look at the definition of the self-tuning regulator problem. We're going to consider a linear system with a state, xt, input ut, and a disturbance wt. And it's going to evolve according to these linear dynamics defined by A star and B star, which are unknown parameters. Here, wt will be a zero mean Gaussian disturbance with identity covariance, and our initial state will be 0. Now, the goal of the self-tuning regulator problem is to interact with this unknown system in order to minimize a cost function ct. Okay, ct will be the sum of the LQR stage cost over capital T time steps. Now, in order to analyze the performance of our self-tuning regulator on this cost, it's helpful to define a baseline level of performance that we can't expect to surpass. In order to do this, we'll define the ergodic LQR cost as the time-averaged LQR cost under a controller K. And this ergodic LQR cost will be minimized by the LQR controller denoted K star. With this definition, we'll define our regret as the cost, Ct, minus T times the ergodic LQR cost of the optimal controller. Okay, so what the regret is capturing here is how much additional cost we're incurring because we don't know the dynamics of the system. To understand how we expect the regret to grow a little bit, I'm going to present a couple of results from prior work that guarantee that if A star and B star are fully unknown to the learner, then the expected regret scales as square root T. However, if we know either A star or B star in advance, then the expected regret will scale as log T. So having some additional prior information can reduce the complexity or reduce the regret. Okay, we'll come back to these regret bounds when we present our own bounds in several minutes. Okay, with that definition of the self-tuning regulator, we'll get into our definition of the misspecified model class. So we're still going to assume that A star and B star are unknown, but we'll additionally assume that we have prior knowledge of some approximate basis of dimension d theta. Okay, and when we say an approximate basis, we mean that A star and B star can be approximately represented as a linear combination of the elements in this basis. To characterize the accuracy of this approximation, we're going to define the subspace distance between the true instance, A star, B star, and the misspecified basis. Okay. The subspace distance is defined as the Frobenius norm of this matrix, where the matrix is the projection of the true dynamics, A star and B star, onto the orthogonal complement of the approximate basis. So some examples of where this might come from are, firstly, you could use first principles knowledge. So you could construct these by hand using physics models. Alternatively, you could use a multitask representation learning approach where you collect data from multiple related systems and learn these matrices. Okay, so with this definition of the misspecified model class, we're ready to present our algorithm. So we're going to start off by assuming that we have an initial stabilizing controller, K0. We have our misspecified basis, and we have an initial epoch length and the amount of time that we want to run our algorithm. We're going to start off by just setting the initial controller we're going to play to that stabilizing controller, and parameter tau0 just as 0. And then we're going to proceed in epochs. Each epoch will be of length tau sub k, where k is the epoch index. And these will be doubling. So the first epoch will be of length c, and subsequent epochs will double the previous epoch. Then for each step in this epoch, we're going to play the controller k hat indexed by the current epoch number, in addition to some exploratory noise. This noise will just be zero mean Gaussian, but scaled by a parameter sigma k that controls the level of exploration during the epoch. Using the data we've collected during this epoch, we're going to estimate the parameter theta hat by solving the least squares problem. In particular, we'll just look over the data collected from the current epoch and minimize the one-step prediction error over the class of models representable by our misspecified basis. Given that parameter theta hat, we're going to synthesize the controller for the next epoch using certainty equivalence. So we'll just treat the parameter theta hat as though the linear combination we get from that are the true dynamics, and then synthesize the LQR controller. Okay, so this just proceeds until the t time steps are exhausted, and we incur whatever regret we get from playing these inputs and observing the states we observed. Okay, so that's the algorithm that we're going to be able to prove bounds about. So let's get to our first bounds. First, we're going to look at a general case without additional strong assumptions on our dynamics. So we're going to let epsilon denote some sort of upper bound on our subspace distance. And we're going to set our exploration schedule as the max between two quantities. So at epoch k, we'll set it between the max of something that decays with the length of that epoch, so a component of the exploration that decays, and then a square root epsilon. So this part does not decay as we proceed. It depends on the level of misspecification, or rather, our upper bound on it. Okay, in this case, we find that the expected regret is upper bounded by the sum of two terms. One is scaling with square root t, and one is scaling linearly in t. However, importantly, the term that's scaling linearly in t is multiplied by the coefficient square root of epsilon. So this is capturing the irreducible error that we get from misspecification. Now, this is under some additional terms and conditions. So firstly, we need an initial epoch length that's sufficiently long. And we also need our misspecification level to be sufficiently small that we can actually get stabilizing controllers from LQR synthesis. Okay, so to understand this bound a little bit better, let's look into the low data regime. So where we have an amount of data bounded by something in terms of the subspace distance. In this case, the regret will be bounded by a term that scales with square root t. And if we compare this to the lower bound that we saw in the beginning of the talk, we note that if our parameter dimension d theta, the dimension of this basis, is smaller than the state dimension times the input dimension, then we actually beat the lower bound that we had in the absence of this misspecified basis in this low data regime. Okay, so to understand when this condition is satisfied, note that it's not immediately satisfied because the parameter dimension could generally be as high as dx times dx plus du, but in many systems, we'll be able to have a low-dimensional unknown parameter that describes our system, or at least approximates it well. Okay, so this is nice, but at the end of the day, it's really just shaving down this dimensional factor from d theta, or from du squared times dx to d theta times du. We ask, is there a condition where we can guarantee a better improvement in the regret that we achieve? And to answer this question, we identify a condition known as the easy identifiability condition, which we say holds if for both our initial stabilizing controller and our optimal controller, the minimum eigenvalue of this matrix is greater than 0. Okay, so this matrix depends on our misspecified basis and also depends on the controller k. Right? And what this matrix is actually representing is a lower bound on the covariance of the features from our approximate basis. Okay, so by guaranteeing that this is greater than 0, we're essentially guaranteeing that the closed loop system under the controller k is persistently exciting. Because of this, the iterations that we perform in our algorithm, where we play the certainty equivalent controller, are persistently exciting as well, and as a result, we can set the exploration schedule to 0. Okay, and in this case, our regret bound improves to log squared of t plus epsilon squared times t. And again, under those terms and conditions on the initial epoch length and the size of the misspecification. All right, let's again examine this under the condition where t is in the small data regime. So for t less than or equal to log squared of t divided by epsilon squared, we find that the regret grows logarithmically. Okay, so what this implies is that, firstly, when we set epsilon to 0, that upper bound on t goes off to infinity, and we generalize the settings where logarithmic regret is attainable in the online LQR problem to systems where that easy identifiability condition holds. Okay, secondly, even if we do have misspecification, we have some coarse prior knowledge due to this misspecified basis, logarithmic regret is achievable in the low data regime. Okay, so with that, let's just look at some numerical validation to guarantee that our regret bounds are actually what we kind of see in practice. And to do so, we're just going to look at the discretized and linearized cart pole system. So the dynamics of this will be denoted A star, B star. These matrices have a total of 20 parameters. However, we note that only 4 of them actually vary as we change the parameters of the cart pole system. As such, we're going to define a 4-dimensional approximate basis. And we find that the easy identifiability condition holds for this basis, so we can play our certainty equivalent algorithm with no exploration. And we compare this to learning from scratch. So we compare using this misspecified basis with varying levels of misspecification artificially injected versus learning A star and B star totally from scratch and using exploration throughout the course of our algorithm. Okay, what we see is that there's a substantial regime of time where using this misspecified basis is actually improving upon the regret of learning from scratch. However, because they're all growing linearly, at least when there is misspecification present, it will eventually do worse than learning from scratch because there is this unavoidable error. Okay, but now if you look at this, you might be wondering where the logarithmic regret is occurring. It looks like it's pretty much just linear. If we zoom in at the very beginning, it's the very low data regime where we actually see this logarithmic regret. After that, the linear term will dominate, but it'll have a very shallow or very small slope. Okay, I'll conclude there. And you can access the paper here to find any additional information. And I look forward to any questions.
Thank you. I think in the interest of time, because we're running a bit over, can I ask for questions to be taken offline after this session? We'll move straight on to the next speaker. Okay, so our next speaker is Aritra Mitra from North Carolina State University. And over to you.
Okay, thank you for that introduction. So this is joint work with my former PhD lab mate Lintao, who's now a professor at the Hwazong University of Science and Technology, and Professor Vijay Gupta at Purdue University. Okay, so this work is going to sit at the intersection of two different areas, network control systems and learning. When one thinks of the classical network control systems paradigm, the idea is to consider control problems subject to some kind of communication constraint. Okay, so and one typical problem in this space is the one that I'm showing you over here, where you have an LTI plant and a controller separated by a channel that can support at most B bits of transmission per use. Okay, now we have a sensor here that's co-located with the plant, and at each time step, this sensor can observe the full state of the system, but when it tries to send over the state to the controller, it needs to do so over this B bit channel. Okay, so the sensor encodes the state using B bits, sends it over, the controller decodes the state and generates a state feedback loop. Okay, and the question that has been extensively studied in this context is how many bits do we need to stabilize this LTI system? And several works have followed up on this by looking at other kinds of channel models where you might have noise, channels that introduce packet drops, latencies, and whatnot. But the running assumption in all of these works is the fact that the model of the system is assumed to be known. And we want to depart from this literature by considering similar questions when the model is unknown. And the broader agenda here is we want to sort of look at the intersection of control, communication, and learning. Okay, so with that broad motivation in mind, let's formally set up our problem of interest. We're going to consider an LTI system that's affected by additive noise, where the noise is IIT zero mean with bounded covariance. And our goal is to find the state feedback controller that minimizes the standard LQR cost. Okay, now if the model of the system is known, we can find this controller using the celebrated Riccati equation. And if it's not known, then as one of the speakers in this session mentioned, Toso, you can run a very simple gradient descent type algorithm where you think of the objective function as the LQR cost and the optimization variable as the policy. Okay, so if one has access to exact policy gradients, then this simple scheme is going to guarantee exponentially fast convergence to the global optimal controller. Okay, so you can think of this as sort of a model-free reinforcement learning approach to the LQR problem. Now, our specific interest in this work is to understand the robustness of this problem in the face of information or communication constraints. Okay, so to examine this, we're going to think of a somewhat stylized setting where, once again, you have an agent and a decision maker separated by a B-bit channel. At each time step, this decision maker is going to send down the current policy to the agent. Now, you can think of this agent as some low-level robot that gets to explore this policy in this world. And we'll assume that based on the observations that are returned by this environment, the agent is in a position to compute the exact noiseless policy gradient. Okay, now, when the agent tries to send this policy gradient over to the decision maker, it again encounters this p-bit channel. So it needs to encode this policy gradient, send it over, and the decision maker is going to use this quantized policy gradient to update the policy. Okay, so that's the setting that I just described. And the key thing to note here is that this channel is essentially distorting the LQR policy gradient. And the question is, despite these distortions, can we still hope for exact convergence to the globally optimal policy? Okay, so this is the question that we want to understand. Okay, so based on this setting, here are our contributions. Our first contribution is to design a new algorithm that relies on the principle of adaptive quantization. And what we prove is that with this algorithm, you can still enjoy exponentially fast convergence to the globally optimal policy. But perhaps what's more interesting and counterintuitive is the fact that if the channel capacity exceeds a certain finite bit rate, then the convergence rate of our algorithm is exactly the same as that of the unquantized policy gradient algorithm. Okay, so the main message here is that above a certain channel capacity, quantization comes for free, and there is no loss in performance whatsoever. Okay. So in the remainder of the talk, what I'll show you are the key ideas that lead to this result. Okay, so to start off, what we're going to do is abstract out the key properties of our problem into a setting where you want to minimize a function f, subject again to communication constraints. Okay, so the idea again here is that you have a server and an agent separated by a channel. The server sends down the current model to the agent. The agent encodes the gradient using bits, sends it over, and you update the model. Okay. And the question that we want to answer here is how many bits do we need to preserve convergence rates? Okay, but to make this question meaningful, I need to have a function class in mind. And for our purposes, the function class that's going to suffice is the class of smooth and strongly convex functions. Okay, so let's recall that a function is said to be L smooth if the gradient map is L Lipschitz. And we say that a function is strongly convex if it essentially has like positive curvature. Okay. So for this class of functions, it's well known that if you were to just run the standard gradient descent update rule with a fixed step size, you can converge to the true minimizer. And importantly, the rate of convergence is dictated by the condition number kappa, where kappa is the ratio of the smoothness parameter to the strong convexity parameter. Now, when we introduce bit constraints into the mix, there have been several approaches that have been studied in the optimization and learning literature, and several quantization techniques have been proposed. And the typical result that you achieve with these schemes is that you're still able to guarantee exponential convergence, but the rate of convergence now takes a hit. So it's no longer kappa. It gets attenuated by a factor delta that's greater than 1, where delta captures the level of compression. So if the fewer the number of bits, the larger the value of delta, the slower the rate of convergence. So based on these schemes, it seems that there is an apparent trade-off between the speed of convergence and the capacity of the channel. So what we wanted to understand is whether this trade-off is fundamental, or could it be overcome if we design our encoding scheme in a more informed way. And it turns out that it's the latter. So what I'm going to do is quickly go over the key ideas that lead to this scheme. Okay, so it relies on two very simple observations. Let's suppose that at iteration t-1, the latest version of the gradient that's available of the server is gt-1. Now using this estimate, the server is going to update the model to xt, and the worker is going to compute the new gradient at this model. Now here's the first main observation. Because this function is smooth, grad fxt can't be too different from grad fxt-1. Right? So if gt-1 is close to grad fxt-1, it must also be close to grad fxt. So the implication is that, well, at the agent, you should really be trying to encode what's new in the gradient at iteration t relative to what's already known about this gradient at iteration t-1. Because that's what we call the innovation in the gradient signal. And the second observation comes from the fact that if we design our algorithm correctly, then it must be that the magnitude of the gradient is becoming smaller and smaller over time. So this means that the gradient sequence should be Cauchy, and the change in the gradient should be small, and hence the innovation signal should reside in smaller and smaller balls. So we should adapt the range of our quantizer to account for the shrinking balls. So all we do is essentially put these ideas together, and the details are available in the paper. But the main thing that I'd like to point out is that this encoding scheme is is exploiting the structure of the problem, and that it's leveraging the smoothness of this operator and the fact that this gradient is eventually becoming small. Okay, so it's not ad hoc. Okay, so what can we say about this scheme? Let's suppose that the function is globally smooth and strongly convex. Then what we can prove is that as long as the channel capacity exceeds a certain bit rate, our algorithm is going to guarantee exactly the same bounds that you get with gradient descent. So importantly, note that this convergence rate here is again kappa. So there is no attenuation factor over here. Now, if you think about the channel capacity here, up to log factors, it's d bits, where d is the dimension of the gradient. And what shows up in the log factor is the condition number kappa. Now, you might ask that, well, you're preserving rates, but is this dependence on the channel capacity optimal? Is it tight? Okay, so the answer to that is, indeed, it is optimal. So if you were to preserve rates, then a lower bound on the channel capacity is precisely of this order. So it's at most away by a universal constant. And this converse result is not due to us. It was proven by Baba Kasibi and Victor Agostino's group at Caltech. So the main message up to this point is the fact that with our approach, you can preserve rates under minimal requirements on the channel capacity. But the question that remains open is, how do we take these results and translate them to the LQR setting? So what was also mentioned earlier in this session is the fact that there are certain challenges related to the fact that the smoothness and the gradient domination condition only hold locally within certain sets, and we would like the sequence of policies to remain within the stabilizing set. So this leads to an interesting tension. Let's suppose that this is the stabilizing set and you're within this set. Now, because the quantized gradient is a distorted version of the true LQR gradient, if the distortion is too high, then even if you begin within the stabilizing set, you might jump outside of it. So one natural way you can think of reducing this distortion is to reduce the step size of the learning rate. But if you reduce the learning rate too much, then this might come at the expense of the rate of convergence. So this is precisely why this question of preserving rates is interesting here. And the main result is that, again, despite these challenges, if the channel capacity again exceeds a finite bit rate, then the convergence rate of our algorithm continues to match that of the vanilla policy gradient. So that's the main takeaway. And this proof relies on a new potential function, a new Lyapunov function, and a careful inductive argument. I'm happy to chat about this proof technique offline. Okay, so let me quickly summarize. What we wanted to do is take the first steps towards combining these areas of network control and learning. To that end, we studied a communication-constrained policy gradient approach for the LQR problem, and we designed a new algorithm that's able to maintain exponential rates under minimal requirements on the channel capacity. So now everything that I said in this talk was for the case where you have noise-less gradients, but you could extend the same things to the noisy setting. This requires more work, but this is going to show up in an archive paper that we'll put up soon. So there are several interesting questions that remain open. In principle, whenever the underlying operator is smooth, and you can potentially apply the scheme. So you can think about what other RL and optimization problems can we think of where this rate preservation applies. You can think about other channel models. You can think about multi-agent settings, etc. And these references are some of our initial works along these thrusts. So with that, I'll stop and I'll be happy to take questions. Thank you.
So again, as we've run over, can I ask you to ask Aritra questions after the session during coffee? So I'd like to thank all of you for attending this session and for all the speakers that we've had this afternoon. Thank you.